So in detecting the different types of decay particles, one thing that's different about them is charges. So different particles are going to react different to different charges. So if I shoot the particles past something with a positive on the top and a negative on the bottom, as it goes past, it's going to be pushed one direction or the other. And that will separate them. So you can separate the beam of particles and see which kinds you have. Okay? So charge will separate them. And actually you look at two things as that charge separates them. The first is which direction they turn. So they're going to turn different directions based on whether what the sign is on their particle, what charge it has, whether it's positive or negative. And the amount it turns depends on the charge. Bigger charges would be repelled or attracted more. Smaller charges would be repelled or attracted less. And also by the mass, because light things are easy to turn, heavy things are hard to turn. So how much it turns is affected by both charge and mass. Okay? So let's see what happens when you do it. Okay, so I've got a source of radioactive source, some generic one, and I'm going to shoot it past the negative on top, positive on the bottom, and see where it ends up. So carbon-14 is a beta emitter. And that's what happens with carbon-14. Why does it turn towards the positive charge? Why would a beta particle turn towards the positive charge? Because it's negatively charged. Opposites attract. Likes repel. It's being pushed by the negative above and being attracted by the positive below. So as it goes between those charges, it's going to turn. Okay? What would happen with a gamma emitter, like strontium, cobalt-60? Cobalt-60 emits gamma as part of the way it gets rid of its energy. Where would the gamma show up? Well, gamma has what kind of charge? None. So how's it going to be affected by the positive and negative charge? It's not. So it's going to go straight through without turning. Okay. What about, you tell me a lot about it. What about radon-222? It's an alpha emitter. Okay. Which way should alpha turn? Well, alpha is a helium nucleus, right? Positive 2 charge, so it should turn towards the negative. So the direction is determined by the charge. What you can't really tell unless you see all three at the same time is there's a difference in how much they charge, in how much they turn. The gamma doesn't turn at all, but notice the beta turned a lot more than the alpha. Why? Okay, well, it has a negative charge, but actually alpha's got a bigger charge. It's positive 2. Alpha's got a bigger charge than a beta particle. It should turn more. It's about size, though. It's twice the charge, but it's also 2,000 times the mass. No, 8,000 times the mass. 8,000 times the mass is a lot harder to turn. Make sense? They left one off here. They left off positron. Where would a positron show up? Would a positron turn up or down? up. How much? It's the same mass as the beta, and it's got exactly the opposite charge, so it's going to turn exactly the opposite direction in exactly the same amount. That make sense? So I expect the positron to be up here. Reasonable? Yeah. So we used Geiger counters. Geiger was one of Rutherford's assistants. He found a way to count radiation. So, because he had seen a lot of alpha particles shining on screens as he was doing Rutherford's experiment over and over again. And the Geiger counter is a device that basically takes that flash that you see on the fluorescent screen and turns it into an electrical charge, which means current will flow, and oftentimes they hook it up to something that makes noise. Okay, so up here, I actually have a Geiger counter. Three, two, one. Okay. And I've got it turned off so we can't hear it right now because this beeping is annoying. Okay. But every once in a while you hear this beep. That means a radioactive particle has gotten inside and it's hit the detector in there. There's always radiation around us. It's called background radiation. We can't get rid of all of it. There's always unstable atoms around everywhere. Okay? So there's always background radiation. But the different types of radiation penetrate different amounts. Okay? So it's only going to be dangerous if it penetrates. Say, what do I mean by different ones do different amounts? Okay. So here I have a couple of radioactive sources. I know they're different types. To tell if they're radioactive, it's making a lot more noise right now. Now it's not. Okay. So those both things have a lot of radioactive particles coming out. Okay. But when I close the lid, just a plastic lid, this one slowed a little bit, but if I put pi plate in between, but if I put the pi plate here, okay, so this goes through the pi plate. Doesn't go through the pi plate as much. There's still some getting through, right? The more pi plates I put, the more it would block. Okay? So different types penetrate different amounts. So different types are dangerous in different situations. Some things it's always dangerous to be around radiation in some fashion, but there's some place we're surrounded by radiation all the time. Your smoke detector in your house has radioactive materials inside it. It's an alpha source. Okay? Why? Well, alphas are easy to block. They're big. So if smoke gets in the way, the alpha particle gets blocked. If the alpha particle gets blocked, your smoke detector goes off. Okay? So we're surrounded by radiation all the time. You just don't always, oftentimes they do it in ways that you don't know because it can be made safe. Has anybody warned you about the radioactive hazards of your smoke detector? No. But there was a young man whose father worked for a fire-thing company. He collected a whole bunch of smoke detectors and built a nuclear reactor in his backyard before they caught him. Backyard nuclear scientist, yep. He built his own nuclear reactor in the backyard.